Okay, this will be the last part of 2.6 here. We're going to start off with the exercises from last time, which was to graph the absolute value of 1 minus x plus 2 and also negative quantity x plus 2 squared minus 4. So let me give just a sequence of graphs, a sequence of events here to get us to where we want to go. So we start off with the absolute value, then we have absolute of x plus 1. We want x to be negative, so we swap x to negative x, and then finally we add 2. So this is a horizontal shift. This part is going to be a reflection. Let me use a different color pen here. This is a reflection across the y-axis. And this last piece is a vertical shift. VS for vertical shift. Okay, so we start off with the absolute value function. Then we horizontal shift to the left by 1. And let's keep a point labeled here 0, 0. So when we go to the left, we're at negative 1. So we have this guy. Then we reflect across the y-axis. And let me erase some of this. I'll come back to h of x in a little bit. Then we're reflecting across the y. So negative 1, 0 becomes 1, 0. And we have this graph. And then we vertical shift up 1 unit. So then finally we go up by 2 units. So we're at 1, 0 becomes 1, and then 2 here. So we have the base point 1, 2, and this is the graph, the final graph of g tilde. Okay, so we're going to do a similar process for h of x, or h tilde. We want to eventually end up with negative x plus 2 squared minus 4. So we start with x squared, then we shift by 2 units to the left, then we negate the whole function, and then we subtract 4. And again, you don't have to do this such stage by stage. In fact, if you're familiar with parabolas in this particular case, you can do it just directly using where the vertex is. But the procedure is generally useful, especially if you're dealing with functions that are not so standard. So let's go ahead and do this. So we start off with x squared, vertex is 0, 0. Shift over by 2 units to the left to get you a parabola pointing upward starting at negative 2, 0. Here, this is a reflection across the x-axis because we're negating the entire function. So let me draw. So when we reflect, we get this guy. Now, and then finally, our final graph here is the following, where our base point, negative 2, and then we go down by 4, 1, 2, 3, and 4. And we have a downward pointing parabola. Okay, so this is the procedure for that particular example. Let's move forward. Again, we're skipping, so we're skipping horizontal and vertical stretches. In the context of polynomials again, when you go to 142, you'll see things called the sine and the cosine function. These things come in much more handy in that context. Okay, so what we're going to do now is talk about, this will be the last part, odd and even functions. The nice thing about this is, in a way, we've already talked about it, but these are essentially types of symmetry of functions. And we talked about, so even functions correspond to functions that are symmetric about the y-axis, and odd functions are symmetric about the origin. So in, I think 1.9, we talked about this. Well, let's talk about it in the context of functions. Remember that, so just a little remark here. Functions, well, I should say most functions cannot be symmetric about the x-axis. And the reason for that, just as an example, if we had something like this, well, this is symmetric about the x-axis, but it doesn't pass the vertical line test. This fails vertical line test, which means it's not a function. Okay, that's why we don't, when we originally talked about symmetry, we had 3 types, but in terms of functions, we're going to focus on these 2 types, because most functions, they can't be symmetric about the x-axis. Probably the types of exceptions that might exist are just if f of x is just 0, meaning identically it's the x-axis itself, but that's like a kind of peculiar exception. Most don't fall into that category. Okay, so how do we already know of 2 examples which are symmetric about the y-axis here, and we already have an example of something that was symmetric about the origin. But how do we come up with conditions that are in terms of the function, in terms of functional notation? So that's what we're going to see right now. So a function, and by the way, this is going to be the even one, this is going to be the odd. A function is even if f of negative x equals f of x. The definition, when you put it in terms of functions, it comes out to be much cleaner. And that's why we like these definitions more than just generically symmetry about the y-axis and about the origin. We say even and odd. And a function is odd if f of negative x equals the negative of f of x. So here you have negative is inside the x, and here the negative comes outside. And I guess we can add that a function is neither if it's neither odd nor even. There's lots of functions like that too. So let's just show by this definition that our x squared and x cubed are actually even and odd respectively. So let's start with, let's show that f of x is x squared using this definition is even. And again, even just means symmetry about the y-axis, and odd is symmetry about the origin. Okay. Well, what do we need to show? We need to show f of negative x is equal to, and eventually we should get equal to x squared, because that's what f of x is. Well, what do we have here? We have negative x squared, which is negative 1 squared x squared, which is x squared. Well, I guess I wrote that twice, which is indeed equal to f of x. Okay, so f of x is even, and we've seen the graph multiple times that means it's symmetric about the y-axis. Let's show that f of x, if f of x is x cubed, then this is odd. And what we have to show is that f of negative x is equal to negative f of x. So what do we want? We want to start off with f of negative x, and we want to end up with negative f of x. Okay. Well, what do we have? We have negative x quantity cubed, which is negative 1 cubed x cubed, and that's just negative x cubed, because negative 1 cubed is negative 1, and that is exactly negative f of x. Okay. And we know the graph of x cubed is something like that, and you can visually see. So here's f of x, here's negative x, this value must be negative f of x, and that algebraic correspondence corresponds exactly to symmetry about the origin. Okay, and remember, symmetry about the origin means, so symmetry about origin means if you reflect across the y-axis and then the x-axis, then you land on, the graph lands on itself. Then the graph lands on itself. Okay. So that's symmetry about the origin, and that corresponds to being an odd function. So the types of problems that you get is given a general function to check. So the problems will be given an f of x. Is it odd, even, or neither? Because all functions are either odd, even, or neither. So let's do a couple of examples and then we'll stop. So let's say we have x squared minus x to the 4th plus 1. We'll do 3 examples. Each one will fall into one of these categories. Let's do x cubed minus 1. And let's do 1 over x minus x to the 5th. Okay, so for each of these, we're going to check whether f of x is odd, even, or neither. So for all of them, what do we have to do? We have to check what is f of negative x. Well, in number 1, we get negative x quantity squared minus negative x to the 4th plus 1. This is negative 1 squared x squared minus negative 1 to the 4th x to the 4th plus 1. And that's exactly x squared minus x to the fourth plus 1. Because negative 1 here, they're all to the even powers. Those become positive ones. And we're left exactly with the original function itself. And hence this function, we started with f of negative x. We ended up with f of x. This is an even function. Meaning whatever the graph is, I don't know exactly what it looks like, but it's going to be symmetric about the y-axis. Okay. Let's look at the next one, where f of x is x cubed minus 1. So f of negative x then is negative x quantity cubed minus 1. This is negative 1 cubed x cubed minus 1. This is negative x cubed minus 1. Now notice that's not the same as the original f of x, right? Because the original was positive x cubed minus 1. So for starters, this is definitely not even. Okay, it's not even because f of negative x is not the same as f of x. Now the question is it odd? So the question is f of x odd? Well, what is negative f of x? This is negative 1 times f of x, which is x cubed minus 1. This is negative x cubed plus 1. So f of negative x is not the same as negative f of x. So note, f of negative x does not equal negative f of x, nor does it equal f of x. So this one is actually, hence, f of x is neither. Okay. So this is an example of one that's neither, and there's lots of these examples. So it's neither, in spite of the fact, by the way, that there was an x cubed to start with. Just because there's an x cubed doesn't mean it's immediately going to be odd. But sometimes the odd powers do work out. So the last one we had was 1 over x minus x to the fifth. What is f of negative x? Well, this is 1 over negative x minus negative x to the fifth. This is negative 1 over x minus negative 1 to the fifth, x to the fifth. There's 5 negatives here and another negative, so overall we're going to end up with a plus x to the fifth. Now notice that this is actually equal to negative 1 times 1 over x minus x to the fifth. If you distribute this negative sign, you would get exactly what we had previously, and that is negative 1 times f of x, i.e. negative f of x. So we started with f of negative x, we ended up with the negative of the original function, hence this is an odd, f of x is odd. So it's symmetric about the origin. Okay, that is the end of 2.6.